Have you ever wondered what's really going on inside your phone or your laptop? I mean, deep down. It feels like magic, but it's not. It's logic. And in this explainer, we're going to pull back the curtain on the simple yet powerful idea that makes our entire digital world tick.
Let's just start with a really simple question, one you've probably thought about before. How does a calculator, a little piece of plastic and silicon, know that 1 plus 1 equals 2? It doesn't have a brain, right? Well, the answer is actually surprisingly simple, and it is the key to, well, everything. So, here's our game plan for getting to that answer. First, we're going to dive into the world of signals. Then, we'll learn the actual language of logic that computers speak. After that, we'll meet the tiny little decision makers called logic gates, see how we can build cool things with them, and finally, wrap it all up with why this stuff truly matters.
All right, first things first. Our journey begins with the world of signals. You see, before any device can think or calculate, it has to get information. And that info comes in the form of signals. And it turns out there are two very, very different kinds. You know, the textbook that really got us started on this whole explainer makes one thing crystal clear right from the get-go. If you want to understand how computers work, you first have to get your head around signals, specifically that crucial difference between analog and digital. This right here, this is ground zero. And this slide just lays it out perfectly. On the left, you've got an analog signal. The best way to think about this is like a dimmer switch for a light. It's a smooth, continuous flow, right? You can have infinite levels of brightness. But on the right, that's a digital signal. And that's just your standard light switch. It's either all the way on or it's all the way off. There is absolutely no in-between. So our entire digital world is built on that simple on or off concept. Pretty basic, right? But how do you turn a light switch into a language? Well, that brings us right to our second section, the language of logic. The answer is something called a Boolean function. Now, don't let the fancy name scare you. It's actually super simple. It's just a system where every single value is either true or it's false. That's it. And we represent true with the number 1 for on, and we represent false with a 0 for off. This simple two-choice system is the entire language of computers. I mean, just stop and think about that for a second. Everything. Your favorite video game, the web browser you're using, the complex algorithm that's recommending your next movie. At the most fundamental level, it is all just a massive, high-speed series of yes or no decisions, a 1 or a 0. That's the whole shebang. Okay, so if this Boolean logic is the language, then what's actually doing the speaking? Well, that leads us right into our next section. Let's meet the logic gates. These are the physical, microscopic building blocks that are making billions of these decisions every single second. A logic gate is, well, it's basically a tiny bouncer at a club door. It looks at the signals, the inputs that are coming in, which, remember, are just ones or zeros, and based on one very specific rule it's been given, it produces a single output, another 1 or a 0. It's a tiny, lightning-fast decision machine. You know when you turn your phone sideways and the screen rotates? That's a decision made by a whole bunch of logic gates. So to make this really concrete, let's just look at one of the most common and simple types of gates. It's called the AND gate, and its rule is super intuitive. This little chart here is called a truth table, and it's a key concept from our source material. Really, it's just a cheat sheet that shows you every possible outcome for the gate. Just look at the output column. See how it's almost always 0 or false? That's because the AND gate's only rule is this. It will only output a 1, or true, if input A and input B are both 1. Any other combination, you get a 0. Simple, right? Okay, now this is where it gets really cool. One little gate by itself can't do a whole lot. But what happens when you start linking them together? Well, welcome to Section 4, Building with Logic. So how do we combine these gates to do something actually useful? Well, our source text points us to the perfect example, building things called half and full adders. An adder is just a circuit that's designed to do one thing, and one thing only, addition. And this brings us right back to our original calculator question. This diagram here shows exactly how it works. You take two inputs, let's call them A and B. They get fed into a combination of a couple of different gates. You can see our friend the AND gate right there, and it's working with another type called an XOR gate. Together, they form this little assembly line that calculates the sum. Just by combining these simple decision makers, you can suddenly do math.
And boom, there it is, the big aha moment. A calculator knows that 1 plus 1 equals 2 because it has circuits made of these simple logic gates that are physically wired to produce the output 2 when you give them the inputs 1 and 1. It's not thinking, it's just physics and logic working in perfect, beautiful harmony. And when you combine millions or even billions of these circuits, you get a modern computer processor.
So why does all this matter? Why should you care about these tiny little switches? Because this one core idea, the ability to reduce any problem to a series of simple yes or no questions, is the absolute foundation of our entire technological world.
So this is the big takeaway. From the smartphone in your hand, to the satellites orbiting the Earth, to the AI that everyone's talking about, the fundamental operating principle is exactly the same. Digital logic is the bedrock that allows us to build all this incredible complexity, and it all starts from that one powerful, simple idea, true or false.
So I'll leave you with this final thought. If all of our most complex technology is built on this ridiculously simple foundation of yes or no answers, what's the next impossibly big question that we can answer just by breaking it down to its simplest parts? Thanks for watching.